The last section in this chapter is section 5.5 on the fundamental forces of nature. Our objectives here are to identify the four fundamental forces of nature and understand their relative strength. We also want to be able to use Newton's law of universal gravitation to solve for some force problems as well. Now, we've applied various forces to problems in utilizing Newton's laws and identifying forces that are acting. All of these were macroscopic, real-world situations. However, there are some other types of forces that we have not yet discussed. Typically, they're forces that are happening on more of a microscopic level. So the question we're looking to ask are, what are the four fundamental forces of nature? And the answer to that is the gravitational force, the electromagnetic force, strong force, and weak force. The gravitational force is obviously one that we've worked with a little bit already. It's that mutual attraction between any two objects in the universe. Though it may seem strong when you're talking about large objects, for example, the gravitational pull between you and Earth being a very large object, gravitational force is actually the weakest force of these four. Newton's law of universal gravitation actually describes how you could figure out that gravitational pull between any two masses, because his law says that every particle with mass is going to attract every other particle that also has mass. That force is equal to a gmm over r squared. M1 and M2 would be representing the two masses in question. Capital G is just a gravitational constant that is equal to about 6.67 times 10 to the negative 11th. Units on that would be Newton meters squared per kilogram squared. So that's just a gravitational constant. R is going to be the distance between those two objects, that separation between mass 1 and mass 2, and that radius or distance is going to be squared. That's why this type of equation is called an inverse square law, depending inversely on the square of the distances between the particles. The second force on our list is the electromagnetic force. This is the force that binds atoms and molecules. It's much stronger than the gravitational force and involves two types of particles, both positive and negative particles. And that means that it can either be attractive or repulsive. Coulomb's law is the one that actually describes this force, and it gives the magnitude of that electrostatic force between any two charged particles. Look at this equation and notice that it is very similar to the one for gravity. This one is K times Q1 and Q2 divided by r squared. So KQQ over r squared is your force of electrostatic attraction. Again, it's an inverse square law, depending inversely on the square of the distance between the particles. So r is still representing distance here. The q's in this equation are the charges of the particles measured in coulombs, or capital C. And the k in this equation is an electrostatic constant. That constant is equal to about 8.99 times 10 to the 9th, and the units on that would be Newton meters squared per Coulomb squared. So again, Coulomb's law describes how this force is going to act when two particles are next to each other and each has some sort of electrostatic charge or sign. The next force that we're looking at is the strong force. The strong force is an attractive force that binds nucleons, basically the pieces of a nucleus, the protons and the neutrons. This is also known then as the nuclear force. This force is much stronger than the electromagnetic force, but it only can act over extremely short distances. Its strength, in fact, decreases rapidly outside of the nucleus of an atom and is pretty much completely negligible anytime you get a distance that is any more than 10 to the negative 14th meters. So it does act over very, very small distances. Now, if this force exists that binds these nucleons together, what accounts for some atoms being unstable? The fact that some atoms, in fact, radioactively decay, and those nucleons will come apart. That answer is what we call the weak force. The weak force is a very short-range force that produces instability in nuclei, and it is key to radioactive decay. This force is 10 to the 36 times stronger than the gravitational forces and 10 to the third times weaker than the electromagnetic force. The current view of fundamental forces is in fact just a little bit more interesting. Physicists have been searching for years to find a simplification model to reduce the number of forces needed to describe the universe. In fact, it is now predicted and even confirmed that the electromagnetic and weak force are actually manifestations of one force that they now call the electroweak force. And the quark model in atoms has also led to the strong force now being defined as a force that binds quarks together, which is now oftentimes called the color force, and that comes from color being a property of these quarks. There's a lot of interesting stuff that you can look at when it comes to these fundamental forces of nature. In fact, if you're more interested in it, you can find more information in Chapter 31 in your book. For our purposes now, in this class and in this chapter, we'll be focusing mostly on that gravitational force and Newton's universal law of gravitation. And then when you come back to class, we'll try a couple of problems and let you see how you can do in working with that.